In this part of the Neurocomputers and Deep Learning course related to deep Boltzmann machine, you will learn what is probabilistic neuron, what are original and restricted Boltzmann machine, how to train a single restricted Boltzmann machine, what is deep Boltzmann machine and how to train it, what is deep belief network and how to use it for pattern generation. Boltzmann machine is a recurrent neural network having stochastic neurons, and its dynamic is defined in terms of energies of joint configurations of the visible and hidden units. We have some visible units and additionally hidden units. All the nodes are connected to each other in the classical Boltzmann machine, and it has symmetrical connections, that is Wij is equal to Wji. In the network, we have stochastic neurons. Each neuron output is set either to 1 or 0 probabilistically. Output updates are applied iteratively in an asynchronous way. In the probabilistic neuron, the probability that neuron I has output 1 is given by the formula. The probability that the output of neuron I to be 1 is equal to 1 over 1 plus exponential in parentheses minus bi minus summation of j sj wji. Notice that this is corresponding to the minus activation of the neuron I. If the activation is high, that means that this value will be small, so the probability increases. If the activation is too large, if it goes to infinity, then probability of that neuron have output 1 approaches to 1. Otherwise, if the activation is negative and large, in that case, we will have a positive large value here. So this part approaches to infinity. 1 divided by infinity approaches to 0. So if the activation is negative large, in that case, probability approaches to 0. So the probability of having 1 is that for very large negative activation values, it is close to 0. And as activation approaches to 0, it has value 1 over 2. And as activation goes to infinity, the value of the probability, the output being 1, approaches to 1. In a Boltzmann machine, a trial for a state transition is a two-step process. In the first step, given a state X, which is concatenation of the output of the visible units and output of the hidden units, among these units, first the unit J is selected as a candidate to change state. The selection probability usually has uniform distribution over the units. In the second step, the probabilistic function is used to determine whether the next state of I to be 1 or minus 1. That is, the activation is calculated, and according to that activation, sigmoid function is applied on the negative of the activation, and the probability is calculated. The energy function for Boltzmann machine is given by this formula. The energy with configuration V on the visible units and H on the hidden units is given by the formula. There is a summation here and minus before that. We have index I element of the units. We are considering the neuron I. Here we have SI, VH multiplied by PI. PI is the bias of unit I, and this SI is the binary state of unit I in joint configuration BH. SI is either 0 or 1. Minus 1 over 2, we are considering all the unit pairs IJ, and we are considering the binary state of unit I and binary state of unit J, and they are multiplied by the weight between units I and J. Because the connection weights are symmetric, if we interchange I and J, we will obtain the same value. After summation is done, it is divided by 1 over 2 because while we are calculating the summation, this connection and the corresponding units are added twice. Again, we have a minus here. If you compare Hopfield network and Boltzmann machine, notice that Boltzmann machine is a recurrent network having symmetric connections. It has some similarities with the Hopfield network. If we consider the continuous Hopfield network, we have an energy surface on the continuous space. Memory elements are to be stored at local minimums of the energy surface. If we are going to use discrete Hopfield network, then these local minimums are going to the corners of the hypercube. Hopfield network is deterministic. At each iteration, the energy decreases and it stops at local minima. On the other hand, if we are considering binary state space, either for Hopfield network and also we have binary state space for the Boltzmann machine, then they are defined on hypercube and these local minima are corresponding some corners of the hypercube. Boltzmann machine operates probabilistically compared to the Hopfield network, which was deterministic. Not each time, but on the average, the energy decreases until reaching an equilibrium, and then it wanders around the local minimum. Probabilistically, it may escape from a local minimum. In the deep Boltzmann machine, instead of the classical Boltzmann machine, restricted Boltzmann machine is used. Restricted Boltzmann machine has two layers. There is no connection within layers, but only between layers. It has two layers, which are called visible layer and hidden layer. There is no connection within layers, but only between visible and hidden layer. This is the only difference from classical Boltzmann machine, that is restriction on the connections. Still, the connections are symmetrical, that is Wij is equal to Wji. Notice that we have only connections between the neurons having different layers. Because there is no connection between the neurons in the same layer, the state update can be done layer-wise as in PAM, that is synchronously. So to find out the neuron outputs here, they are calculated at once by using the output values of the neurons at the visible layer. And notice that their activations are calculated, and then the output values are determined probabilistically. If we are using restricted Boltzmann machine, energy function can be simplified as, again, we have energy with configuration V on the visible units and H on the hidden units is equal to, this part is same as in the classical Boltzmann machine. We have output of the neurons are multiplied by biases, and then there is a summation over all the units, either visible or hidden. However, this second term is different. Instead of 1 over 2 here, we have I as chosen from the visible units and J is chosen from the hidden units. Because of that, each pair is considered only once and there is no need 1 over 2 before the summation. In restricted Boltzmann machine, connectivity is restricted to make inference and learning easier. We have a single hidden layer and we have visible layer. There is no connection between the units within the same layer. There's only connection between visible and hidden layer. In restricted Boltzmann machine, the hidden units are conditionally independent given the visible state. It only takes one step to reach equilibrium when the visible units are clamped. So we can quickly get the exact value of Si multiplied by Sj, the output of the neuron I multiplied by the output of the neuron J, and we are looking at what is the expected value of multiplication of this pair. And this is going to be used in training. For training a single restricted Boltzmann machine, we start with a training vector on the visible unit as step 0. And then by using the output values of the neuron in this layer, we are finding out what are the activities of each neuron in the hidden layer. Then the outputs are set probabilistically considering the activations of the neurons. Once we have found the outputs of these units, each one is either 0 or 1, then by using these values, similarly, we are finding out what are the outputs of the units in the visible unit by calculating the activations using the outputs of the neurons in the hidden layer, and then by calculating the probability, the values of the outputs of these neurons are set. After these are set, this is repeated to find out the outputs of the hidden neurons, and whatever done 4 times 1 is repeated 4 times 2, and this goes on at time infinity. The output of the neurons at the visible layer is called a fantasy. Then for each pair here in the visible unit and hidden unit, SI, output of neuron I and output of neuron J, we are finding what is the expected value. This is corresponding to step 0, and this is repeated for step 1 and up to step infinite. These expected values are calculated by repeating this operation several times. These expected values of SI-SJ pairs are used in determining the change in the connection weight. It is set as a learning rate epsilon multiplied by the expected value calculated here for SI-SJ at 0 minus expected value of SI-SJ pair at infinity. Notice that this weight update formula is requiring updating the outputs of the neurons several times to obtain value of the outputs of the units at a large iteration. To speed up the process of training restricted Boltzmann machine, contrastive divergence learning is proposed. It's a quick way to train a restricted Boltzmann machine. Start with a training vector on the visible units. Update all the hidden units in parallel here. Update all the visible units in parallel to get a reconstruction. So from the outputs of the neurons in this layer, we are calculating the outputs of the neurons in the visible layer again, probabilistically, and this is called a reconstruction. We are updating the hidden units again. So we have iteration 0 and then iteration 1. This is not following the gradient of the log likelihood, but it works well. It is updating the weights Wij by considering epsilon learning rate multiplied the expected value SI-SJ at step 0 minus SI expected value of SI-SJ at step 1 instead of using a fantasy at iteration infinity. We are considering the expected value at step 1. Here we have a restricted Boltzmann machine. At the visible layer, we have 16 by 16. That means 256 visible units and 100 hidden units are used for the hidden layer. When this model is trained by using the patterns corresponding to digit 2, then after training completed, when data is applied at the restricted Boltzmann machine, it will produce reconstructed data at the visible layer, which are similar to pattern 2. However, if this input data is applied as input to a model trained with the samples from a data set containing only representation of the digit 3, although the pattern 2 is applied, it will reconstruct some patterns which are resembling digit 3 instead of 2. Up to now, we considered only a single restricted Boltzmann machine. However, if we are going to use deep Boltzmann machine, then we have a pre-training step in the deep Boltzmann machine, training a deep network by stacking restricted Boltzmann machines. First, train a layer of features that receive input directly from the input, pixels, etc. Then treat the activations of the trained features as if they were pixels and learn features in the second hidden layer. Then do it again for the next layers. So it is trained layer by layer. First, train a restricted Boltzmann machine by applying the patterns on the visible units. And after this network is trained, then apply a pattern, obtain outputs at the hidden layer, and copy this binary state H1 for each state on the visible unit. Then train another restricted Boltzmann machine. Here we have the values transferred from the hidden layer, and we are using this layer as if the visible unit and the other layer as the hidden layer. Let the connection weights obtained by training the first RBM be W1 and the connection weights for the second RBM be W2. Compose the two RBM models to make a single deep restricted Boltzmann machine model. So here we are copying this connection weights to the restricted Boltzmann machines here in a layered manner. Here we have connection matrices W1 and W2. If we consider the forward direction, we are considering transpose of the connection weights, but in the reverse direction, we are using the W1 itself. And only downward connections are used. It is called deep belief network. In order to use deep Boltzmann machine for recognition, for discrimination, on top RBM, use also label units L, shown here. Here we have first hidden layer, the second hidden layer, obtained by training the restricted Boltzmann machine, and this may be repeated for several hidden layers. And at the end, for the last layer, we are adding label units. On top RBM, use also label units L. Use K label nodes if there are K classes. A label vector is obtained by setting the node in L corresponding to the class of the data to 1, while all the others are 0. And we have here one more hidden layer. Train top RBM together with these label units. When a pattern is applied here, these labels are clamped to the corresponding code as defined here. Train the top RBM together with the label units. The model learns a joint density for labels applied here and images applied in the visible layer. For recognition, apply a pattern at bottom layer. By using the forward directions, find out the outputs of hidden neurons here. And then, by using this recurrent network, observe the values for the labels. Then the expected value of the outputs of the units observed here can be used to find out what is the corresponding class for the applied pattern. Deep Boltzmann machine may be used also for generation data. Use generation connections, that is, recurrent connections here, and also downward connections. W3 here is recurrent, W1 and W2 is feed forward, goes only in one direction. Clamp L, the output of these neurons, to a label vector, and then get an equilibrium sample from the top level RBM by performing alternating Gibbs sampling for a long time. For this purpose, use green connections, and then in the second step, perform a top-down pass to get states for all other layers using the blue connections. The lower level bottom-up red connections are not part of the generative model. We are not using the connections going up for the generation. The patterns observed at V layer corresponds to generated data. A deep neural network model of digit recognition and modeling using restricted Boltzmann machine. Using deep Boltzmann machine can be reached at this address. In this one, handwritten digits in the study, handwritten digits are collected on 28 by 28 pixel images for digits from 0 up to 9. We have 10 classes, so we have 10 label units. 500 units are used for the first hidden layer, another 500 units for the second hidden layer, and here for the third hidden layer, there are 2000 hidden neurons. A fine-tuning can be applied on the deep Boltzmann machine as first learn one layer at a time by stacking restricted Boltzmann machines. Treat this as pre-training that finds a good initial set of weights which can be fine-tuned by local search procedure. We don't have labels, but stacked restricted Boltzmann machines are trained, and after that add a 10-way softmax at the top and do backpropagation. So this becomes a feed-forward network which is initialized by the connection weights determined by training the deep Boltzmann machine layer by layer. Some applications using deep Boltzmann machine on speech recognition can be found at this address, and also another one trained to discriminate cats and faces can be found at this address.